April 12, 1942, Richmond, California. The western edge of the shipyard lies beneath a haze of smoke and salt air. Sparks fall in constant rhythm along the hull of a half-finished Liberty ship. The dock cranes move in deliberate arcs above the shoreline, their steel arms groaning as they lift prefabricated hull sections into position. A horn sounds once every hour to mark the end of a shift, though no one stops. The work continues through the signal. Rows of welders move in pairs, each one hidden behind a mask of darkened glass. The sound is steady, a mix of electric hiss and hammer strikes. The smell of burnt flux and oil drifts over the bay. A foreman checks a clipboard marked Section 48B. The record shows that this hull segment should have been completed 3 days earlier. A missing piece in the schedule column is marked only by 2 words, gun failure. Inside a corrugated shed near Dock 3, a team of engineers examines a pile of discarded welding equipment. The standard torches are bulky and prone to clogging after long use. Each unit must be cooled manually with a bucket of water. In the wartime schedule, even a 30-second delay multiplies into days. A mechanic named Fred Brandt leans over the workbench, holding a smaller, improvised tool made from leftover aircraft parts. He turns it over in his hands, a crude, pistol-shaped handle with an integrated wire feeder. The design looks like a child's toy beside the industrial torches lined along the wall. It lacks the heavy copper nozzles of standard models. The insulation is rubber from a tire tube. The engineer's notes describe it as unfit for sustained use. One supervisor wrote, "Stupid gun, impractical in field." The unit was returned to the shed for scrap. Beyond the fence, the scale of the shipyard has doubled in less than 6 months. Rail cars arrive hourly with steel plate, valves, and bolts. Each new ship demands over 500,000 welds. By the spring of 1942, production has reached a physical limit. Even with 3 shifts, assembly times stall at 42 days per vessel. The U.S. Maritime Commission warns that without a new method, the Atlantic convoy schedule cannot be met. In the mess hall, men discuss rumors of a mechanical replacement for manual welding. Someone mentions a prototype gun that feeds its own wire, like a sewing machine, one worker says. Another laughs. Too delicate. Won't last a night shift. Outside, the rain begins to fall on stacked steel panels, the drops hissing as they hit the heated metal. Floodlights stay on past midnight, illuminating workers through a mist of steam. At Pier 5, the half-completed ship SS John Henry stands suspended in scaffolding. Its hull plates show hundreds of chalk marks where joints remain unwelded. Every unsealed line means another day at the dock. Inspectors from the Maritime Commission walk along the catwalks, noting the delays. The ship's foreman closes his logbook and looks toward the dim light in the fabrication shed, where Brandt is testing his unapproved welding gun once more. The records for that night mention an anomaly in current readings, a continuous arc sustained for 45 minutes without cooling interruption. No failures reported. No cracks observed on test metal. The entry ends with a brief notation, operator used non-standard device, performance exceeded expectations. By morning, the shed door remains locked. Workers entering the yard notice a single welded strip of steel on the test bench, smooth, even, and uninterrupted. The kind of line that would normally take 3 men an hour to complete. No one yet realizes that this single experiment, dismissed as a stupid gun, will soon cut the nation's shipbuilding time in half and change the industrial power of the world's navies forever. By late April 1942, word of the self-feeding welding gun has reached the main assembly floor. The device is not approved, not catalogued, and not insured. Yet the production chief orders a demonstration. Engineers gather near the test platform beside Dock 2. The atmosphere is dry and metallic, filled with the rhythmic impact of pneumatic hammers. Brant steps forward wearing a standard face shield. The gun in his hand is compact, connected to a spool box mounted on a wooden crate. A thin wire runs through the handle and out the nozzle. A foreman from the commission checks the voltage meter and signals to begin. When the trigger is pulled, the arc ignites with a clear, steady hiss. The wire feeds automatically, burning at a precise rate. No pause, no separate rod change. Observers watch in silence as the weld flows smoothly along the test plate. The bead forms evenly, uniform in width and depth. Most notice the absence of downtime, no stops for wire replacement, no cooling delay. One engineer marks the stopwatch. 2 minutes, 17 seconds. A comparable joint using standard torches had taken nearly 12. Someone murmurs, continuous arc feed. Another, it won't last on ship steel. The test continues. After 40 minutes, the first cooling break is called not for the gun, but for the operator's fatigue. The metal remains intact, free of porosity. The inspector signs the page, successful under non-standard conditions. That afternoon, a memo circulates through the Richmond Yard Engineering Office, subject, portable continuous feed gun, field potential. It notes the unit's reduced weight and one-hand operation. Suggested uses include confined spaces, bilges, hull interiors, and deck undersides, where traditional equipment cannot fit. The author, listed as F. Brant, requests further material testing and permission for field integration. By May, a small batch of the devices is fabricated from spare aviation components. Each carries a handwritten tag, Model 1B, wire feed arc gun. They are distributed to a handful of welders on the night shift of Pier 3. Records describe a noticeable drop in daily stoppages. Workers finish joint lines previously requiring multiple relays. Photographs taken by commission inspectors show the guns lying among standard torches, smaller, lighter, connected by thin cords instead of thick hoses. In the images, the welders appear crouched inside ship hulls, the light from the arc reflecting off their helmets. The process seems effortless. In the background, cranes lower new sections into place without waiting for the previous welds to cool. The field reports begin to accumulate. Reduced warping, one states. Improved penetration consistency. Another highlights a new phenomenon, welders working continuously through full shifts without replacing rods. The data charts reveal a 37% improvement in line completion rates across test docks. Still, resistance remains. A senior engineer from the Bureau of Ships writes that the design is unorthodox and likely unstable under marine stress. Yet the yard's output tells a different story. 2 ships, Hiram Johnson and Benjamin Goodhue, are completed ahead of schedule by 6 and 9 days respectively. The anomaly is traced to the teams using Brant's gun. On May 28, the U.S. Maritime Commission issues a limited authorization, provisional use approved for non-critical joints. The instruction is clear, only secondary welds may employ the device. But welders quietly use it everywhere. By June, more than 50 units are in operation. The production charts begin to curve upward, tracing the invisible signature of a rejected invention now driving an industrial revolution. In the foundry at midnight, Brant tests a refined version built with surplus ball bearings and a wire tensioner from a bomber turret motor. The feed is smoother, the weight balanced. A colleague records the voltage readings, steady, consistent, and efficient. As sparks fall against the concrete floor, no one speaks. They all understand what they are witnessing, not theory, not experiment, but a tool that allows ships to be built as fast as metal can be delivered. By July 1942, the Bureau of Ships begins compiling comparative figures between manual and wire feed welding. The data shows a consistent pattern: average hull welding time reduced by 42%, arc-on efficiency doubled, and electrode waste nearly eliminated. The report carries no headline, just a simple line in typewriter ink: continuous feed apparatus displays exceptional throughput under repetitive task conditions. At the Richmond and Kaiser yards, the numbers translate to production milestones never before achieved. Where a Liberty ship had once required 1.2 million labor hours, it now averages 680,000. In practice, that means one new vessel every 5 days, an industrial rhythm previously thought impossible without automated machinery. The sound of construction changes accordingly. Instead of the pause clang of rod replacement, the yard becomes a single unbroken hum, the steady breathing of electricity through steel. Photographic archives show the new guns distributed by the crate load, each stamped with the stenciled initials WF. Within 2 months, over 1,000 units are in service across the West Coast. Bethlehem Steel requests technical blueprints. General Electric's tool division files a patent application, not for the gun itself, but for the feed mechanism, which it calls a continuous consumable electrode system. The War Production Board lists it as non-classified, allowing unrestricted replication. In Washington, the Maritime Commission's August Bulletin makes a brief reference: new self-feeding weld guns contribute to improved ship output, now under formal adoption for naval use. No name is credited. The same bulletin lists record completion rates: 57 ships in a single month, more than all Axis powers combined. The technical data is unambiguous. Weld quality is uniform, joint failure rates drop below 1%. Heat distortion, a chronic problem in continuous hull seams, is minimized by the controlled wire feed. Independent testing at the Norfolk Naval Yard confirms identical tensile strength between standard and wire-fed welds. For the first time, mass production of seaworthy hulls becomes a measurable science, not an art sustained by skill alone. Inside the yards, workers refer to the new tool by nickname, stupid gun, half in irony, half in pride. It is faster, lighter, and burns hotter. Welders learn to adjust current by sound rather than gauge, listening for a distinct crackle that signals proper wire speed. Supervisors note that training times for new recruits fall from 3 weeks to 4 days. With every improvement in speed, another metric shifts: costs decline, output rises, and idle time disappears. Across the Pacific, Allied convoy strength begins to climb. The U.S. Navy reports that by early 1943, the fleet gains a net tonnage of 1 ship for every 2 lost. Admiral Land of the Maritime Commission writes privately, "Our true weapon is not steel, but continuity." That continuity comes from a device born in a scrap shed, its concept dismissed by nearly every engineer who saw it first. In September 1942, production managers at Kaiser's Oregon yard send a cable to Washington, request immediate scale-up of wire feed arc equipment for emergency ship program. 2 weeks later, the War Department authorizes mass manufacture under the classification welding gun, portable, continuous feed, Type B. Over 40,000 units are ordered. Archival inspection films from that autumn show Liberty ships sliding into the water one after another, each hull numbered, each rivet replaced by welds too clean to distinguish by eye. The sound of launching ceremonies overlaps with the constant hammer of fabrication. Workers stand on dry dock rails coated in slag dust, watching another vessel join the convoy line. No speeches, no applause. Just the mechanical certainty that another would follow in days, not weeks. By the end of 1942, the United States has built more ships in a single year than in the previous 25 combined. Production analysts trace the turning point to the moment when welding stopped being interrupted. The night a rejected stupid gun burned through its first test plate and never once stopped for cooling. By 1944, the docks at Richmond and Portland no longer echo with pauses. The shipyards operate like continuous circuits, energy flowing in shifts around the clock. From the catwalks, the scale looks unreal, parallel hulls in all stages of completion, sparks cascading in synchronized arcs, cranes moving like clock hands across the skyline. Aerial reconnaissance photographs taken for the War Production Board show geometric order, ships aligned in identical rows, weld seams glowing under floodlight. The stupid gun is now regulation issue. Its shape has changed, more compact, housed in aluminum, with an integrated spool drum. Production manuals call it the Hobart Wire Feed Assembly, Type 23. Every major yard carries them by the thousands. Manuals detail wire specifications, amperage limits, and cooling cycles, yet the essence remains the same as Brandt's improvised prototype, uninterrupted current, continuous motion. According to Bureau of Ships records, this change reduces average vessel delivery times to just 24 days. In the Richmond yard alone, 3 ships are launched every 2 days. The phrase "Victory Fleet" enters official correspondence. Engineers stop referring to welders by name, they are listed as production units, assigned by gun serial number. Wartime footage from 1945 shows Liberty ships, tankers, and landing craft filling harbors like assembled components of a vast machine. No rivets, no seams, just welded lines that shimmer in sunlight. Inspectors who once doubted the process now certify hulls faster than they can be painted. The gun has removed the final bottleneck in industrial war, human rhythm. Machines and men now move at the same pace. Post-war, the numbers remain staggering. In less than 4 years, American shipyards have produced 2,710 Liberty ships, 531 Victory ships, and hundreds of tankers and escorts, all built with wire feed welding. Every one of them a product of uninterrupted process. Allied supply losses drop, convoy tonnage doubles, and the Atlantic routes remain open. After Japan's surrender, the Maritime Commission disbands much of its emergency program. Warehouses full of welding guns are packed in crates labeled surplus, do not return. The public never hears their story. When reporters tour the shipyards, they focus on the scale, not the tool that made the scale possible. The innovation is buried under statistics, absorbed into the myth of American industrial power. Fred Brandt never patents his design. The wire feed mechanism becomes standard across every manufacturing discipline, from automotive assembly to aerospace production. In 1946, General Electric files an internal memorandum noting that continuous consumable electrode technology now underpins the company's post-war product line. No mention is made of its origin in a shipyard shed. In later years, naval engineers reviewing wartime methods will describe the period as a conversion from craft to continuity. The gun that began as an unapproved modification has effectively replaced centuries of manual welding technique. The precision and uniformity it introduced become the foundation of modern fabrication, from nuclear submarines to aircraft carriers. At the Richmond yard, the cranes are silent now. The docks serve as storage for decommissioned ships awaiting scrap. Wind moves through the rusted rails once covered in molten slag. In a maintenance shed still standing near the bay, a single welded strip rests on a shelf, labeled only Test Plate 1B. The weld line runs perfectly straight, dull with age but unbroken, a trace of the moment when a stupid idea welded together not just steel, but the machinery of a global navy. By early 1943, the War Production Board begins standardizing industrial methods for every major shipyard under its jurisdiction. The wire feed gun, now listed in official manuals as Continuous Arc Unit, Portable Type B, is shipped east for trials at Bath Iron Works and Newport News. Engineers from the Bureau of Ships record the same findings: fewer weld defects, less material waste, faster cooling cycles. The process no longer depends on operator strength or stamina. Machines determine the tempo, and men follow. The results are immediate. Atlantic yards once considered slow or outdated match West Coast output within months. The SS John P. Gaines, completed in Maine, records the fastest Liberty ship assembly on record, 5 days, 20 hours, from keel to launch. Newspapers attribute the feat to American teamwork. Internal documents tell a simpler truth: uninterrupted arc welding allowed for the first continuous build cycle in shipyard history. At the Kaiser facilities, process engineers adopt a phrase that becomes doctrine: no idle arc. They reorganize entire assembly lines to keep electricity flowing 24 hours a day. To support it, steel suppliers switch to pre-cut sections, pre-drilled mounts, and uniform joint spacing, all designed around the efficiency of the wire feed system. The stupid gun has quietly restructured an entire logistics network. The transformation spreads beyond shipbuilding. Aircraft fuselage plants in California request units for experimental production of bomber components. Tank factories in Michigan adapt the gun to high-carbon armor plate. One Army Ordnance report from March 1943 observes that the same tool which sealed the Liberty fleet now binds our armored divisions. Meanwhile, the original inventor remains a minor figure. Fred Brandt, still employed as a maintenance technician, is noted in personnel logs as consultant, electrical apparatus. He oversees maintenance of the production line that now operates without pause. The shed where the first gun was tested becomes an equipment storehouse, its walls blackened by years of arc flash. By 1944, production reaches a point of near automation. Welders work in relay teams, handing off live units between shifts without powering down. Overhead cameras record the glow of thousands of simultaneous arcs, each moving at constant speed. Supervisors track progress not by ships, but by linear feet of weld completed per hour, a metric made possible only by continuous feed design. Naval analysts call it industrial compounding. Each new ship built increases capacity to build the next, as cranes, slipways, and workers are freed in a recursive cycle. No other nation manages to match it. German yards remain dependent on manual torches and riveted sections, while Japanese production suffers under labor shortages and slow manual methods. In effect, the United States has mechanized time itself. Photographs from 1945 show the scale fully realized, hulls arranged in parallel rows stretching beyond the horizon. Above them, banners red wheel deliver the goods. On the ground, every welder holds a compact gun, each identical in form. The moment of discovery has long passed. What remains is system, repetition, and output measured in tons per hour. After the war, the same technology migrates into the private sector. Car frames, oil pipelines, bridges, all adopt the continuous feed method. Technical schools rewrite their curricula, replacing hand welding instruction with motorized units. Within a decade, manual rod welding becomes a specialist craft, preserved only in repair work and training demonstrations. Government correspondence from 1946 contains a short paragraph buried in an appendix. The transition to continuous feed arc systems represents the single most significant advancement in modern ship fabrication. The principle of uninterrupted process remains the foundation of American industry. In post-war documentaries, the innovation is rarely mentioned. Narrators focus on the men, the ships, the vast industrial mobilization. Yet behind every frame of fire and light lies a single mechanism that never stopped moving, a wire spool feeding into a gun once called useless, now the unseen hand that built the mightiest fleet in human history. Spring 1946. The war is over, but the machinery keeps running. The docks that once built destroyers and Liberty ships now fabricate merchant vessels, oil tankers, and deep-sea trawlers. The same floodlights still burn at night, illuminating empty slipways where new ships rise from recycled steel. The wire feed guns remain in use, their cords patched, their spools replaced, their function unchanged. The U.S. Maritime Commission's final audit lists a figure so large it seems abstract: over 5,777 ships built using continuous feed welding. The cumulative welded length exceeds 16 million linear feet of seam, enough to circle the planet. Yet no monument or press release mentions the invention. The gun is treated not as innovation but inevitability, absorbed into the baseline of industrial progress. In Washington, engineers from the Office of Naval Research study how wartime methods might serve peace. One memo notes, the continuous arc principle reduces human downtime and ensures consistent structural integrity. Potential applications: aerospace frames, automotive assembly, civilian shipbuilding. Within 2 years, the technology spreads beyond the docks. The first mass-produced cars welded entirely by machine appear in Detroit. Boeing introduces automated arc systems into aircraft production. The technique evolves, not through new theory but refinement. Manufacturers integrate automatic voltage control, internal wire spools, and inert gas shielding. These advances transform the crude wartime gun into the modern MiG and TIG systems still in use today. Each improvement carries the DNA of that first improvised tool: the stripped-down handle, the constant current, the principle of motion without interruption. In 1950, the Bureau of Standards officially defines the process as gas-metal arc welding. The documentation includes voltage charts, electrode specifications, and current flow diagrams. It omits the origin story entirely. No mention of the night shift shed at Richmond, or the worker who built the first working prototype from aircraft scraps and a salvaged motor. Industrial historians later identify the quiet lineage. They find Brandt's early sketches in a 1941 maintenance ledger and match them to the later commercial patent drawings filed by Hobart and General Electric. The similarities are exact. The gun shape, the feed angle, even the wire tensioner are identical. In the archival photographs, Brandt stands at the edge of a group of welders, uncredited, his name handwritten on the back of one print. By the early 1950s, the same principle drives the Cold War arms race. Submarines, carriers, and nuclear reactors depend on continuous feed welding for pressure hulls and containment vessels. It is no longer experimental or controversial. It is assumed part of the invisible framework of modern engineering. At the Richmond site, the original buildings decay. The slipways are silent, the cranes frozen where they last turned. In 1959, the city repurposes the land for cargo shipping. Few remember what the structures once produced. But under layers of dust, one test bench remains. On it rests a single, preserved tool, small, worn, and marked with the initials FB scratched into its handle. A curator from the Smithsonian visits years later. He photographs the gun and notes its construction: steel tubing, aircraft trigger, copper wire spool, non-standard grip. He writes, an early example of portable continuous feed welder, likely handmade. The tag attached to the photo reads, origin unknown. The irony is complete. The device that built the world's largest navy is now anonymous, its legacy hidden in plain sight, every weld on every modern vessel a silent continuation of the line it first drew. The stupid gun never received credit, ceremony, or patent. It simply worked, and in doing so, redefined how humanity joined metal to metal, and how industry learned to move without stopping. By the 1950s, the American public no longer speaks of welding as innovation. It has become background, the unseen infrastructure of peace. Newsreels glorify the men who built ships, not the tools they held. Wartime propaganda evolves into patriotic nostalgia, posters of sparks and sweat, workers framed as anonymous silhouettes under banners reading "Built in America." The mechanism itself, the self-feeding gun that enabled it all, disappears from the narrative. Film reels from the period reinforce this silence. In government documentaries like Freedom's Forge and Victory at Sea, the narration praises production speed but never explains its cause. The camera pans across miles of welders, their arcs flaring in rhythm, the soundtrack swelling with orchestral triumph. The audience sees motion, not method, light without the hand that shaped it. Within engineering circles, however, the effect is unmistakable. Naval architects begin designing hulls specifically for welded construction. Structural beams, bulkheads, and keels are simplified for linear continuity. The welding gun defines the geometry of post-war shipbuilding without ever being named. Shipyards in Britain, Canada, and Australia license the American process, calling it automatic feed arc welding. German firms adopt it for reconstruction, applying the same method to bridges, trains, and pipelines. In American labor history, the innovation receives no attribution. The Smithsonian's 1957 catalog on wartime production credits advancements in welding techniques, but lists no inventor, no prototype, no single origin point. The assumption is that such progress emerged naturally, as if invention were inevitable once the need existed. Fred Brandt retires quietly that same year. His personnel file lists 31 years of service, position, maintenance technician, electrical equipment. There is no record of commendation. Academics studying industrial psychology later note that anonymity was built into wartime production. In an economy where invention served collective victory, individual credit was often seen as vanity. The stupid gun fit perfectly into that system, useful, efficient, and invisible. Meanwhile, the philosophy it embodied, uninterrupted process, spreads everywhere. In 1954, General Motors introduces the world's first fully automated welding line, assembling one car every 53 seconds. Ford follows. Boeing adopts similar systems for jet airframes. Shipyards evolve into production complexes where human welders guide machines rather than perform the work themselves. The logic of continuity, born in wartime urgency, becomes the default language of industry. In the archives of the Maritime Commission, one overlooked memo dated 1943 summarizes the entire legacy in a single sentence: welding has ceased to be an art, it is now a flow. Those words could apply to every post-war economy built on continuous output, from the conveyor belts of Detroit to the reactors of Hanford, from steel plants in Japan to assembly lines in Germany. Today, in the preserved remains of the Richmond Yard, visitors walk through the Rosie the Riveter National Historical Park. They see posters, tools, photographs of women at work, yet not one display mentions the self-feeding welding gun. The museum text describes manual arc welding as the dominant method of production, a quiet historical error repeated in every guidebook. The gun's physical legacy survives only through function. Every modern MIG welder, every robotic torch, every automated seam carries its principle. The same uninterrupted current flows through modern industries that owe their existence to it. The idea remains alive, stripped of origin, stripped of name, immortal through use. As decades pass, historians revisit wartime engineering archives searching for overlooked origins. They find scattered memos, voltage graphs, and a few grainy photographs labeled non-standard equipment, superior results. They find no patent, no award, no inventor's name. Just performance data, perfect welds, zero downtime, continuous current. And so, the record stands silent. The world's mightiest navy, built on the back of an idea no one thought worth recording. Winter, 1960. The Pacific fog moves inland across the silent yards at Richmond. The cranes stand fixed against the skyline, cables swaying gently in the wind. Along the concrete slips, the outlines of weld lines still catch faint morning light, long seams of dull silver running straight to the edge of the bay. Each one traces the same signature, continuous, unbroken, precise. The last Liberty ships rest at anchor, now cargo freighters for a peaceful world. Few remember the pace at which they were born. Inside the former fabrication shed, dust covers the benches where sparks once flew without pause. In one corner, a cabinet remains locked. When opened decades later, it holds a single prototype gun, the rubber handle cracked, the wire spool corroded to dust. A tag hangs from its trigger, Model 1B, continuous feed apparatus. Returned, April 1942. The handwriting is faint. The letters Def Brant are still visible beneath the smudge of oil. By then, the technology has evolved far beyond recognition. Industrial robots now weld with infrared guidance. Undersea cables and orbiting satellites are sealed by automated arcs controlled by digital sensors. Yet the current that flows through them, steady, measured, self-sustaining, is the same one that first burned through a scrap of ship steel 20 years earlier. Historians of technology debate how such origins vanish. Some say it is the scale of wartime effort, where personal invention dissolves into collective momentum. Others suggest that anonymity was its own kind of victory, that progress required no signature. But the records themselves tell the story clearly enough: production doubled, weld failures vanished, fleets emerged faster than they could be sunk. The cause is written not in speeches or patents, but in voltage logs and daily reports. At the Smithsonian's Materials Division, the gun is eventually catalogued under miscellaneous welding equipment, circa 1942. It is placed on a shelf between obsolete rivet guns and pneumatic drills. No display, no label of significance. Yet every industrial historian who examines it notes the same feature: the wire spool built directly into the handle, the unmistakable design of the first modern wire feed welder. Across the bay, container ships glide past the old yard. Their hulls are seamless, their decks welded in continuous runs that span hundreds of meters. The principle remains unchanged: motion without interruption, energy without pause. The same continuity that built the wartime fleet now drives global commerce, pipelines, and aircraft frames. The world still runs on that same unbroken arc. According to declassified Maritime Commission summaries, the adoption of the wire feed gun shortened the war by an estimated 8 months through industrial acceleration alone. The statement appears once, in a post-war production review, then never again. No photograph of Brant survives beyond a group shot taken near Dock 3 in 1943, 30 men in helmets, faces obscured by soot, the caption reading simply, "Welding Crew, Richmond Yard." In the end, the story resolves not as invention, but as continuity, a single current passed from one generation of engineers to the next. A device dismissed as stupid became the foundation of every metal structure built since. It turned craft into process, repetition into endurance, and light into progress. The yard is quiet now. Wind moves through the skeletal frames of cranes and empty warehouses. Beyond the chain-link fence, a faint hum comes from a ship being repaired at the modern port, a welder's torch, feeding its own wire. The same sound that once built empires. The same rhythm of electricity, steady and endless, that began with one rejected tool and the idea that metal, like time, could flow without stopping.